So today we're going to be talking about infinite geometric series, but before we get to that, we need to talk about infinite limits. So last semester we did investigate infinite limits and we developed some different rules. So I'm going to remind you of those, and we're going to look at a couple new cases that you haven't seen before. So first thing we're going to do, let's consider the limit as n goes to infinity of something pretty simple, so just 1 over n. Okay, if we were to generate some terms, this would be, 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. And a good way to look at limits is graphically. So this is going to be n, that's 1 over n. So I'm going to say that's 1. Okay, so if I were to plot just some of these terms, so 1 over 1 would be 1, 1 over 2 is 1/2, 1/3, 1/4, 1/5, and so on. So what happens here is these values, as the denominator gets bigger and bigger and bigger, goes to infinity, the number itself gets closer and closer to 0. So we say that the limit as n goes to infinity of 1 over n is 0. So the first type of limit that we're going to review is limits of rational functions. So if we have a polynomial over a polynomial. So for the limits of rational functions, it depends on the degree of the numerator and the denominator, whether the degrees are the same or they're different and the top is bigger versus the bottom is bigger. So we're going to investigate all three cases. The first case we're going to look at is if the degree of the numerator is less than the degree of the denominator. So we're going to investigate 2n squared plus 4 over n cubed minus 1. So what we can do is plug in bigger and bigger values to see what is happening as we go to infinity. So I'm going to use the calculator to do this. Okay, so in the calculator, this very first one, and these are all the ones that I'm going to do, and they're from the notes, is 2x squared plus 4 over x cubed minus 1. So I'm going to go to my table, and I'll just show you. I have it set up so I'm going to ask so I can plug in whatever numbers I want. So if I go to my table, I want to plug in, let's say 10. Okay, and we get 63 over 3, fine. Let's plug in 100. We get 0.02 if I plug in 1,000 or 10,000. 2e negative 4, which is basically 0. So what's happening is these numbers get bigger and bigger and bigger. Same number. Okay, they're getting smaller and smaller and smaller. So if the degree is bigger on the top, or degree is bigger on the bottom, the numbers are going to grow faster and faster. So it's going to go to 0. So this one's limit. So the limit as n goes to infinity of this is going to be 0, and that's always going to be the case if the degree is smaller on the top than it is on the bottom. All right, so case number 2 is the switch of that, if the degree of the numerator is bigger than the degree of the denominator. So this time we're going to take that same one I just did, but I flipped it. So we've got n cubed minus 1 over 2n squared plus 4. So you can see now I'm looking at the flip. So x cubed minus 1 over 2x squared plus 4. So now I can plug in different values. 100 is 33333. Let's go 8,000, 40,000. Let's go 100,000, 50,000. Okay, and it's just going to keep getting bigger and bigger and bigger, which is always going to happen in this case. So if we look at this limit, the limit as it goes to infinity, the degree is bigger, it goes to infinity. We also call that does not exist, because for a limit to really exist, it has to go to a single value, and infinity is a location, it's getting bigger and bigger and bigger. But we would say that limit does not exist or is undefined. All of those would be ways to describe this limit. So the last case is if the degrees are equal. And I'm going to look at two of them just to illustrate the idea here. So the degree for this one, we've got a squared over squared. Here I've got a 3n cubed, so this is a degree 3 over degree 3. And we'll use the calculator to look at both of those. So the first one we're going to look at is the 3n squared minus 1 over 4n squared plus 7. So if I plug in 10, we get, well, that one always shows fraction, but we'll plug in some bigger ones. So 0.749, 0.75, 3/4. So 0.75, 3/4, that shows a pretty clear pattern there. Let's look at our other one. So that one went to 3/4. This one, let's say 20, we get negative 0.5. 200 or 2,000, you get negative 0.5. So that's a pretty clear pattern again. So again, negative 1/2. So the first one went to 3/4. This second one went to a negative 1/2. And where that's coming from, if we look, it's coming from the coefficients in front of the highest degree. So we call the leading coefficients. So here, this 3/4, we got a 3/4. Here, we had a negative 1 over a 2, is where we got the negative 1/2. So if the degrees are the same, it's going to depend on whatever those leading coefficients are. So to summarize the three conditions, if the degree of the numerator is smaller, so small over big, then the limit's going to be 0. If the degree is bigger on the top, then the limit does not exist because it goes to infinity. And then if they're the same, it's going to be the ratio of whatever those leading coefficients are. So now we're going to look at a second case, and this one's going to be new, but we're going to be able to come up with a conclusion pretty quickly. If we're taking some number raised to the n power. So the two examples we're going to look at are 2/3 to the n and 3/2 to the n. So first we're going to look at 2/3 to the n. So we just have that one highlighted. So here, I already plugged in, I'll do this. If I plug in 1, we get 2/3. If I plug in 2, 0.44. If I plug in 10, we get 0.0173. 50 is 1.6 to the negative 9, which means we have a decimal followed by 8 zeros and then a 1. Let's say we have 100. We have 18 zeros before we get, or 17 zeros before we get to that 2. So these get very, very small. Versus if we do the other one. So now we're looking at 3/2 to the x. And we do 1, we get 1.5, 2, 5, let's do 10. 100 gives us 4.1 times 10 to the 17. Okay, and then it just gets too big. So these ones just keep getting bigger and bigger and bigger. So 2/3 to the n went to 0. 3/2 to the n went to infinity or does not exist. And it depends on what the number on the inside is. So 2/3 is a number that's less than 1. 3/2 is a number that is bigger than 1. And that's what's going to determine the limit for an exponential function like this. So if the base is a number between -1 and 1, so this will work even if we have negative values, is going to go to 0. It's going to continue to get smaller and smaller. If the number is bigger than 1, then it's going to go to infinity or does not exist.